All right. Hi, everyone. Thanks for joining us for webinar 9, Managing for Water and Soil Structure as part of the Soil Health Training Program webinar series. Today's Tuesday, February 13th. I wanted to thank the Lake Champlain Basin Program and NUIPIC for the funds for this webinar series. Today, we'll go through the usual course overview, quick homework review, and then we'll hand it over to Joshua Faulkner, who will give a lovely presentation for all of us. Thanks for being here, Joshua, and then we'll go over the stuff for the next class. Quickly, where we are, we're at webinar 9 of 12, and so we're at Managing for Water and Soil Structure. Next week, we'll have Integrated Pest Management. And we are very close to having all 4 summer workshops planned. As soon as I have all 4 dates, I will make sure everybody has those on their calendars. And we'll get to explore some things out in the field, which will be wonderful. Quick homework review. Hopefully folks were able to read chapters 14, 15, and 17 out of our textbook. If you haven't, I do recommend going back and reading them. They were quick reads, very interesting, so please do take a look at that. And then with that, I will introduce our presenter. Joshua Faulkner is a research associate professor, director of the UVM Agricultural and Environmental Testing Lab, and coordinates the Farming and Climate Change Program and the UVM Extension Center for Sustainable Agriculture. He does applied research and outreach on soil, water, and nutrient-related issues across the state and provides technical assistance to farmers on practices and innovative solutions to improve the management of these resources. His work spans from the farmstead to the watershed scale. He has a BS in Biological Systems Engineering from Virginia Tech and a MS and PhD in Biological and Environmental Engineering from Cornell University, all with a concentration in soil and water resources. With that, Joshua, I'll let you take it away, and I'll interrupt if there's any pressing questions in the chat. Otherwise, we'll wait to your breaks.
Thanks. I appreciate it, Lauren. Let me get my screen sharing going here. It's minimized. Let me try this. Can't get to my start the show button. Let me see.
I think if you go, you're down in like the bottom left or the bottom right corner next to the
yeah, the Zoom toolbar is blocking it. I can't see it.
Oh.
How do you move the Zoom toolbar? And then I could.
You should be able to click and drag it, and if not, if you go up to slideshow,
yeah,
you can also get it that way.
Okay.
Sorry about
perfect.
That.
Yeah, no, thanks. Okay.
Looks great on my end.
All right, good. All right, thank you, Lauren. Again, good to be with you. And this is one of my most favorite topics, soil and water science. So excited to do this, and really we could spend an entire semester on the topics at hand. But we only have 2 hours. So what I've done is I've divided this into 3 roughly maybe 35 minute sections with a break in between for some Q&A and bio break and that sort of thing. Hopefully we'll be able to get through it. We'll try my best anyway. So just a quick outline. We'll start with soil texture, then we'll talk about soil structure. We'll talk about the process of infiltration, the process of percolation, and the process of runoff, and really kind of in the context of how these are affected by management. But there's also some core concepts that I think we all need to, it might be helpful for some to have a refresher on, and then helpful for others to kind of get up to speed with a little bit of 101 before we talk about management. And then I'll talk about compaction, I think a really important issue here in the Champlain Basin, and then a little bit on irrigation, Not a tremendous amount because it's not a topic that we deal with a lot in the basin, but we certainly are in Vermont, but it certainly is important for specialty crop growers, and there's a growing interest in irrigation. I'll say that. So I'll talk about some of our research there, and then drainage, which is a big topic, especially given years like 2023 when it just rained cats and dogs. Okay, so let's jump right in. So soil texture, and I'm going to need to move Zoom toolbar here again. Get it out, hopefully. Okay, so soil texture, that's where for me everything really starts when we're considering soil and water relations and how water moves through soil. Texture is such a dominating characteristic of soils, and put simply, texture is really just the percentage of sand, silt, and clay within the soil. And this is a textural triangle, USDA's textural triangle, which some of you may have seen, and it's really kind of a neat little tool. You kind of, once you do a textural analysis of your soil, you slide on the various vertices of the triangle based on the percentages of the sand, silt, and clay, and you have your soil texture. That of course ranges from clay to silt to sand, and then sandy loam, clay loam, all these things in between. So the texture is a really important factor, and I think it's helpful to understand the relative size of the various soil constituents that make up soil texture. So in relative, especially in their relation to one another. So sands are, in a relative sense, are very large. If we kind of think of them in comparison to silts, which are very small, they would be the size of a barrel compared to the size of a dinner plate. And then clays are very, very, very small. They would be the size of a coin compared to those, that barrel and that dinner plate. So in these relative sizes play important roles within lots of both soil chemistry and within soil water relations, and they factor heavily into soil structure, which is really our next topic here. And soil structure, by definition, is the combination or arrangement of primary soil particles. And those primary soil particles, again, are those sand, silt, and clay constituents, into secondary units or PEDs. And these secondary units, I think we could, for our purposes, really define as aggregates, as soil aggregates. And soil aggregates, I think about those being a broad term, and really we have micro aggregates, meso aggregates, and macro aggregates, the same way we have microstructure, mesostructure, and macrostructure within soils, and they all play different roles in water movement, and the things that move with water, right? The pollutants and the colloids and things. And so I'm just showing some electron microscope images there on the right-hand side of your screen of microstructure, and you can see, we think of soil, like if you think of those constituent particles, those sand, silt, and clay, you think, oh, it's just this inert stuff, and it's all kind of just stacked into the matrix, and it doesn't really have any structure beyond those particles. But even at the micro level, we have plating occurring, we have webs of mineral particles that form. We have just all this really like very meaningful and important structure, even at the micro level. And a lot of this is I think there's really kind of still science that's exploring the interactions within these within the sites and in the microcavities within this microstructure. And then it's not just, of course, these particles arranging themselves on their own. It's really biology that's playing a very important role in arranging these soil particles into into the microstructure and the mesostructure, the macrostructure. And these are some really, I think, fascinating images of what we would think of, and we'll talk about here in a few minutes, of preferential flow paths, of kind of macro pores within the soil, but these are at a micro level. So these are channels with which air and water can move readily, and these are formed by biology. Really, these are formed by roots within the soil. And then here's an image of a micro aggregate, and so these are those sand, silt, clay particles that are bound together by organic substances into small soil crumbs, right? So this is just a micro image of one of those. And then we move on up quickly to the things we can see right in the field, and that would be our soil aggregates, what we would conventionally think of as soil aggregates, and those are what I kind of think of as being the mesostructure of the soil, and those are lots of those micro aggregates that are bound together, again with organic substances such as glomalin to form soil crumb and really create what we often both visually and physically interpret as a healthy soil when we see these aggregates, and these aggregates are what contributes significantly to soil structure as they kind of fill the matrix in. And of course, they don't, when we have these aggregates, they don't pack in tight against one another. There are voids in between these aggregates, and those are the channels with which air, and in our case today, water moves. So these aggregates are critical for that movement. And here's just another image. This is from a farm in South Hero, Vermont. A farmer that took this over pretty degraded and abused land, and really brought it back to life with some rotational grazing practices. And I just think this is a fantastic image of aggregates, and really the biology that helps to create those aggregates, those earthworms there. And then we can move on up to, that was our mesostructure, and then we can move on up to our macrostructure of soils. And this is an old image, but I think is a really good one, and it kind of outlines some of the I guess basic categories of macrostructure, from granular to prismatic to massive to single grain, blocky, and platy. And then you can see the water droplets in these images, and those are those are intended to indicate how readily water moves through these soils based upon their macrostructure. And you can see a granular or single grain structure. You have very rapid water movement through those. Then on the opposite end of the spectrum, this massive structure, platy structure, water moves very, very, very slowly through these types of structures. So it's just very important to understand what the health of the mesostructure, the health of the soil aggregates in your soil when you think about water movement, what we're about to jump into next, infiltration runoff, but also understand that macro structure as well. And texture will be an important consideration in both of those structures. Okay, and then one last slide here, a kind of basic structure slide, soil density, and so how do we quantify soil structure? And really, density is probably the easiest way to do that in practice. And we typically use something called bulk density. There is the particle density of soil particles, and that would be of an individual sand grain. What's the density of that grain? And typically we're 2.65 grams per cubic centimeter for actual soil material. But when you look at this soil in place, and how much of that volume of soil is contained in void space, that's what defines bulk density. And we typically take this with a ring, kind of cylindrical, a long cylinder of that's made of metal, and hammer it down into the soil and then excavate it out. And then we cook off the water and weigh that soil and the volume, the mass of the soil, and they're divided by the volume of that cylinder as our bulk density, and it can be highly variable and significantly influenced by management, as you might imagine, as these structural factors are. Okay, so that's our little bit of a review on texture and structure, and now let's jump into the process of infiltration. And infiltration is defined as the passage of water into the soil surface, and I think it's important to differentiate this from percolation, which we'll talk about here in a moment, which is the movement of water down through the soil. But these are different processes. Infiltration is when water enters the soil. And so there's different considerations at play and different factors that affect that than affect percolation. In particular, infiltration is affected by precipitation duration and intensity, soil texture and structure, soil moisture content. What's the moisture content of the soil before the rainstorm occurs is what affects how that moisture content affects infiltration. And then soil management. Really, the ones we're going to talk about today are soil texture and structure, and then soil management. We've already addressed a little bit of the texture and structure factors. So I need to move my slide or my toolbar here. Infiltration, what's the impact of soil texture on infiltration rates? And as you might imagine, because we have these different sizes of soil particles, those different sizes of particles stack, if you will, say stack, kind of pack into the matrix and create different levels of void space, where sands have pack in the matrix and have lots of void space. So there's we have very fast infiltration rates versus a finer textured soil like a clay or a loam. And those have very much lower infiltration rates. And I think another important thing to understand about infiltration, and really especially as we kind of move into runoff, is that if the soil, if we are given a dry soil, a relatively dry soil, that infiltration rates when we first have rainfall on that soil are actually very, very rapid. We have the soil actually creates somewhat of a vacuum we call soil tension as it dries out. And when we first have rainfall, the soil actually sucks the water in until it satisfies that soil tension. And then we achieve in time this steady state infiltration rate. But the initial rates of infiltration can be very, very high, but then they level off after time. So it's rare to have runoff when we first. That's one reason why it's rare to have runoff when we first have a onset of precipitation, because we have such high infiltration rates when the storm first starts. Okay. All right, great. And then let me, soil cover and infiltration. I use this slide a lot. There's been a lot of work done on how just basic cover of the soil, whether that's living cover or dead cover, functions to help increase infiltration and decrease runoff. And I think that's maybe I'll just kind of stop for a moment to make that point. You know, that really when we think about at a very coarse scale, that runoff would be the inverse of infiltration, right? Whatever we don't infiltrate runs off, and whatever runs off does not infiltrate. So we have this kind of we can look at this issue of reducing runoff in a very different way. If we look at it as trying to increase infiltration, then we start to kind of look closer at the processes by which we do that. And soil cover is one of those management techniques with which we can use to increase infiltration. And like I said, this is just one example. There's lots of work done on this as we increase just physical cover on the soil. It increases infiltration. And then why does that soil cover help to increase infiltration? If you think about, we have these aggregates of those constituent particles of the sand, silt, and clay. They're on the surface of the soil. And then we have raindrops hitting those aggregates, falling out of the sky at actually a fairly high velocity. And then when they hit those aggregates, it's like, if you kind of imagine the cartoons when a meteor hits the surface of a planet and it just blows chunks everywhere. That's what happens when a raindrop hits those aggregates. If they're not really stable aggregates, it blows them apart into their constituent particles. And those particles, the individual sand, silt, and clay particles, settle back onto the surface. And when they do, they fill in the pore space. And you create what's called surface sealing. And so, and when you have surface sealing, I'm sure many of you, whether you've realized it or not at the time, you've probably witnessed this. Often in the middle of the summer, when it's very dry and your garden's suffering and you need rain and you get a ferocious downpour and you think, oh, thank goodness, and you walk out to the garden and you pick back the bare soil and oh my gosh, it's a half-inch down, it's dry as a bone. None of that water made it through the surface crust. That's what's happening when we have surface sealing, especially on unstable, weakly bound aggregates or uncovered soil. We get this crusting occurring, or surface sealing occurring. Okay. Management effects on infiltration, right? And there's been a tremendous amount of work on this. I just have a few very simple slides on how management affects infiltration rates, and this is a very basic one, where we have a sod, a cultivated soil, and then a cultivated soil with crusting occurring or surface sealing occurring. You can see that there can be multiple times higher infiltration rates in a covered soil that is managed to promote good soil structure. A sod versus a cultivated, especially a cultivated soil that has weak soil aggregation. I apologize, my slides are not advancing. Okay, there we go. And so when we think about that structure, really, we're trying to promote good soil structure for lots of pore space, for water to flow move into the soil and then down through soil. So reduced the less we disturb that structure, the better off we'll be in terms of their ability to get water to infiltrate into the soil. And so in terms of management practice, this means using conservation tillage techniques that are anything less than that full moldboard plow, flip the soil on its head and destroy every single bit of structure within that soil. Anything other than that is really could possibly be classified as conservation tillage, and there's lots of different degrees of that: no-till, zone-till, strip-till, ridge-till. There's others. There's vertical till. There's just all these different things. But the goal of all of these is really to reduce disturbance of the soil and to some extent maintain some soil cover. But and that reduction of disturbance reduces the amount of disruption we do to biological habitats too, and the biological organisms are what are building that structure to begin with. So, it's really twofold when we reduce disturbance. We reduce physically destroying the structure of the soil that's currently exists within the profile. And then we also avoid a disruption of biological habitats within the soil, so that and they take time to reestablish themselves. So it really works in two different ways. And then organic matter. also affects infiltration. And this is a study done in tomato production where all management was all the same except for the type of fertility source. And this, in two plots, there was a high organic matter fertility source used, like compost. And then in one plot, excuse me, there was a low organic matter fertility source utilized and managed through the growing season. And then there was these folks did a rainfall simulation. I just really like how this shows all other things held equal, this organic matter can help increase infiltration as well, because it really provides and I know you've reviewed organic matter, but it again, just as a refresher, it provides the active carbon fraction of organic matter, provides the food for the biology that's really creating that structure that's building soils that have lots of a capacity to infiltrate water. Okay, next is percolation. And as I said, percolation is different than infiltration. Infiltration's the entry of water into the soil, and then percolation is really the vertical movement of water through the profile. And this is percolation is maybe less important as we discuss runoff, but later on when we think about irrigation and drainage, percolation becomes more important. And I just want to review a few key concepts around percolation now, since we're discussing infiltration. Percolation is necessary for leaching to occur, right? So leaching is the movement of dissolved constituents down through the soil profile, often to groundwater. If we don't have percolation, then we can't have leaching. Deep percolation would be defined as water moving below the root zone of the crop and into groundwater. Several factors affect percolation, including soil properties, moisture content of the soil, and the geology of the soil. And I just like this section view of a soil profile where you can see the different water fluxes represented by arrows. And you can kind of see the root zone, the area of the soil between the root zone and the saturated layer of the groundwater table. And then the capillary fringe. And I think that's important to note, especially in our region, because the capillary fringe is where I think we all understand what that might look like when you take a paper towel and you dip it into water. You see the capillary rise of water rising up into the paper towel, right? That's capillary rise. And it's affected by the diameter of the pores in the soil. And so in our clay soils, especially in the Champlain Valley, we have very high capillary fringes because we have really small pore space within that soil because the soil particles are so small. And so that capillary fringe can rise fairly high. And that affects drainage, which we'll discuss later, where in the sandy soil, very narrow, very thin capillary fringe within that soil. Okay, so a few important terminology percolation and soil water that I think are good to note. And again, maybe more relevant to later slides on irrigation and drainage, but these are really, I think, important to understand kind of key concepts. So the first one is field capacity. And this is really the water content of the soil after it's done draining. And so if you I'll show a slide later where someone's dipping a sponge into water and you kind of lift that sponge up out of the bucket of water, and the soil and water drains out of that sponge until it stops. And at that point, that's what happens in soil too. When we have a heavy storm event, the soil saturates, but then it drains over the course of 24 to 48 hours. And that point at which it stops draining, the moisture content of the soil at that point is known as field capacity. And that's really dependent upon the texture of the soil. And then the water that's left, so you have that sponge which you've kind of picked up out of the water, and it's drained. And then if you pretend you wring that sponge out with your hands, the water that it then comes out as you wring that sponge out, that is water that's available to plants And at the point that you can't wring any more water out of the sponge, we'll just pretend our hands represent the water that a plant is pulling out of the soil. That's our permanent wilting point. That's the point at which plants can get no more water out of the soil. The point where we cannot wring any more water out of that sponge. And so the water between the filled capacity and the permanent wilting point is the available water capacity of the soil. And this is highly influenced by the soil texture. And so if we want to understand for irrigation purposes how much water is available for plants within a given soil, we would use this measure of available water capacity. And it's used within the soil survey. It's used in the irrigation literature and kind of extension literature around irrigation. And these all relate to percolation because we have this downward movement of water to first get to filled capacity. So I know that's a lot. Please welcome to ask questions on that at the break. And here's just I think this is a really good graphic of what I just explained in the last slide with the written definitions, that if we start from the right-hand side, moving to the left, we first start with a saturated soil. Water drains out of that due to gravity until we reach filled capacity. Then we have capillary water within the soil, and this is the water that plants can utilize. And then after they're done utilizing water, we've reached our permanent wilting point, and there's still water held within the soil. If you kind of imagine that sponge, after you wring it out as much as you can, it's still moist. But that's hygroscopic water, and that's water that can't be accessed by plants because it's held too tightly within the soil pores. Okay, and then of course, with every rule, there's an exception to the rule, right? So we have this percolation occurring because of gravity, and we're draining the soil profile. All that's well and good, but then we have preferential flow, and I would argue that preferential flow is not the exception to the rule, especially in the Champlain Basin, but is maybe the rule because of the types of soils we have. And preferential flow is really the movement of water down through macropores or cracks within the soil, and it moves water very rapidly downward. This is an image from my old lab at Cornell before my time, but when some of the first work was being done on preferential flow, they would take a ring, and this is in the orchards off campus there, and they would pour dyed water into that infiltration ring and then excavate with a backhoe. And you would expect to see this kind of even front of water moving downward, where the dye kind of covered all the soil as it moves down through the profile. But that's not what occurs, especially and this is key, in a well-structured soil. Well-structured soils are where we typically find preferential flow paths. And that's this, you can see these streaks of dye or streaks of water that moved very deep into the soil profile after the water was applied. Preferential flow paths are often a result of reduced disturbance. And I'll talk a little bit about kind of the pros and cons of reduced disturbance, I think after our break here. And they can be biopores formed from roots or biopores formed from earthworm burrows and things like that, or soil cracks, which are we have in the Champlain Valley. And I do have a good video there. I'm not going to be able to show it. I'll forward it around later on, but it's a awesome demonstration of, in a no-till soil, putting a smoke machine into the end of a tile and pumping smoke into that tile line 3.5 feet underground, and the smoke just rising up through the surface of the soil, 70 feet away from the smoke machine, because there's so many biopores within the soil. So you can imagine what that means for water movement within that soil. It's not flowing through the matrix like we typically would think of with percolation. It's moving very rapidly. And we see this in Vermont. This is what I think makes our soils so interesting to study, is because we have so much preferential flow occurring. That's my boot, size 12 boot beside a crack in Bridport, Vermont, in a dry summer, and this was in a hayfield, in a kind of a depression in a hayfield, but we dumped almost 250 gallons of water just right there in that beside my boot, and it never filled up because we have these amazing crack networks within the soil. And this was an undrained soil, an untiled soil, but this preferential flow paths, which I'll talk about in our third section, also have unfortunate trade-offs for tile drainage, because they can transport water rapidly to tile lines within the soil profile. And then, of course, just maybe this is more of a little bit of trivia there. We think of preferential flow really happening in well-structured soil, but it's also been observed to occur in poorly structured soil like sands. And in sands, we call it finger flow. And this is actually some of the transport of pesticides in Long Island was believed to occur this way, where you have these streaks of flow down through a sandy profile instead of a nice even flow. So just a little bit of trivia there, and a really cool image showing this type of finger flow. Okay, we're about 35 minutes in, so I think we're doing good on time, and I built in a little bit of break here before we move on to our next topics of runoff and erosion.
Thanks, Joshua. Yeah, folks, please put some questions in the chat if you have them, or feel free to come off mute. I've got two questions for you. The first being, can water break up soil aggregates once it's percolating, if it's moving too quickly or something like that? I know obviously it can cause surface crusting, but does it have a negative impact when it's moving through the profile?
Yeah, that's a complicated answer. And I would say yes, it does, especially in preferential flow paths where you have larger channels in the water where water can pick up velocity. We see erosion of, if you can imagine kind of that channel down through the soil, erosion of the walls of that channel, and that then take soil with the water as it moves on down through the profile. Does that make sense?
That does, yeah.
Okay. Yep.
That's really cool.
Great.
And then my second question was just how does slope factor into all of this? All the diagrams are always flat, nice, level fields, but how does slope factor in?
Good question, and it's perhaps unexpected. So if you measure the infiltration rate of a soil, slope does not affect that. Its slope only affects the velocity of the water. If it does not infiltrate, then it starts to pick up speed. And as it picks up speed, as it flows over the surface, it has less opportunity to infiltrate. But if you look at a flat soil and a soil at a slope, really those soils have the exact same infiltration rate. It's just, if the infiltration rate is exceeded and water starts to run off, less of that water is going to soak into the sloping soil because it's moving so rapidly down the slope.
That is really interesting and definitely not the answer I expected. So I'm glad I asked the question. I'm not seeing any other questions in the chat at this point. So if you'd like to keep going, I think we're ready to learn some more.
Sure. Okay. Sounds good. Okay. So now I think I'm going to move on to runoff and erosion, and then a brief cautionary tale about possible trade-offs related to reducing runoff and erosion, especially in phosphorus-sensitive watersheds. And so we see erosion, I kind of have a few slides here of gully erosion that I've taken and have people send to me and collected from across giving extension presentations and such in the region. And this is me standing in a cornfield in Williston. I use this slide a lot in presentations. Some of you may have seen this. This was after one single storm in the summer of 2014 or 2015 in Williston, Vermont. And I'm about 6'2", 6'3", so this is significant erosion here because it's almost up to my hip pockets on my jeans. And I mean, honestly, I studied soil science in school, soil and water science, and had not seen erosion in agricultural fields outside of studying the Dust Bowl. So this was kind of a really special moment. Unfortunate for the farmer, of course, but very interesting. And this is just a few years ago, caught some gullies that had freshly formed in some fields in Addison County. There were at least 2 or 3 just like this over the course of a quarter mile on fairly level ground, to be honest. But this was quite a gully as well. This is an image of severe erosion from Prince Edward Isle. I was able to traveling there, and there's a lot of potatoes grown there, and they have fairly erosive soils, and this is and really growing on pretty low sloping land. And this is it's a little tough to see, but this is just tremendous erosion that they document up there. And then this is the one that beats all. This is just across the Vermont border in New Hampshire, close to the Connecticut River in southwest New Hampshire. This is during the summer, I believe summer 2020 or summer of 21, July of August, they received 30 inches of rainfall in there, this area, and just amazing amounts of erosion. Once those head cuts start on those gullies, they really eat away the head of the gully and churn out underneath the lip, and then the lip collapses, and it just that gully just continues to work further and further up into a field. Okay, so runoff. So really, I think as a hydrologist, it's important to kind of like, people use different terms for runoff, and so I just want to like take a quick second to differentiate between the two ways runoff is used. When we're thinking about watershed at the watershed scale, that's often called total runoff, and that's really what comes out of that watershed in surface waters and rivers and streams. But really, what we're talking about, I think, for air purposes, related to soil health and in agricultural fields and kind of thinking about edge of field runoff is surface runoff. And that's simply put the portion of rainfall that does not evaporate or infiltrate, and that is not subsequently exfiltrate, but that's a kind of an aside there. We don't need to get into that. Factors affecting runoff: of course, precipitation, duration, and intensity. When the precipitation rate exceeds the infiltration capability of the soil, that's, again, going back to this kind of how tightly linked runoff and infiltration are, right? If it doesn't infiltrate, it runs off. If it didn't run off, then it infiltrated, right? Watershed characteristics affect runoff. And so the size of a watershed, the shape of a watershed, the soil conditions with the soil texture and type, the soil moisture content, the topography, geology, ground cover, and land use, which is what we're going to primarily focus on, which are man-made intervention, or how man manages that watershed to affect runoff. And like I said, in general, factors that enhance infiltration serve to reduce runoff. So let's start with texture. And I think the best way, the best kind of shorthand we use for how texture influences runoff is really the Soil Survey's hydrologic soil group. And if you're not familiar with that, it's a 4-tier ranking system, A, B, C, and D, with A soils being your lowest runoff potential soils. And those are your sands, loamy sands, or sandy loam types of soils. And I have significantly shortened the definitions of these, but to just bring to the top how texture is factoring into these different hydrologic soil groups. But there are some other factors that affect these definitions as well. B soils are your moderately low runoff potential soils, silt loams and loams. C soils are your moderately high runoff potential soils, sandy clay loams, and your D soils, which we have a lot of with our clay soils here in Vermont, are your clay loams, silty clay loams, sandy clays, silty clays, or clays. So good to be aware of this ranking system and understand what category if the field in question falls into, because this will be a really kind of give you a good estimate on how much runoff you would expect coming from that soil, from that field. Okay, land use effects on. In general, on a watershed scale, runoff volumes, as you might expect, increase with greater percentage of impervious area in the watershed. That's as we urbanize a watershed, we greatly increase the amount of runoff we see from that watershed. As we put concrete in a barnyard or in a farmstead, we greatly increase the amount of runoff we see from that farmstead because it's impervious surface. That's pretty intuitive. And then our management and variations within land use type and variations within that management also impact runoff. And that's really the levers we have to pull, right, in terms of soil management. We can't change the texture. Oftentimes we're not really in the business in agricultural fields of changing the amount of impervious surface, but we can affect the different degrees of management that's implemented there. And this is again, an old figure, but it still holds true, how management influences infiltration and therefore runoff. And I like to show this because you see such a dramatic difference between starting at the top, an old permanent pasture or heavily mulched field, all the way down, almost an order of magnitude to the very bottom, which is a bare ground that's crusted, that has surface sealing occurred on that soil. Just a tremendous, difference given the same field, just with different management. It makes a tremendous difference in the amount of runoff that's produced. And you can see, we have different lengths of time in permanent pasture towards the top. We move into our haze or grazing systems that are heavily grazed, and then our cropping systems, our cultivated systems towards the bottom. And this is, this would be different for every soil type. And this is a slide I've chosen to put in here to kind of highlight the influence of management, excuse me, on runoff and this rainfall runoff simulator. I used to have one of these that I carried around. This is from the panhandle of West Virginia, the Chesapeake Bay, when I used to work there. And this was, if you're not familiar with these tools, you can take a tray full of soil undisturbed as much as possible, and you can place that tray on the tabletop, and that tray has perforations in the bottom of it. And you can then rain on these soils when they're on the tabletop. There's a sprinkler that's outside of the frame above the frame here, and it has a pretty intense rainfall rate. And then they're on a slight incline, so that when runoff is produced, it comes off the front and it's captured in the front bucket there. And if it if it infiltrates and percolates through the soil, it's captured in the rear bucket, which is kind of tucked back under the table. You can just kind of see that there. But I just love this comparison on the left and in the red square here, red rectangle. These two soils were taken not 2 feet apart from one another in a cornfield, and all I did was add some cover, some straw mulch on one of those, and then rained on them. And you can see what a difference this made in the amount of runoff that was produced and the amount of infiltration and percolation that occurred. You can see full runoff bucket on the left, full infiltration bucket on the right, and vice versa for the back bucket on the left and the front bucket on the right. And then the amount of really the important bit, one of the important bits is the amount of soil and of course nutrients that come with that runoff. And it's just, it's fascinating. It just, to take a process that occurs at a field scale or watershed scale, landscape scale, and shrink it down so that you can actually see what's happening at that larger scale is really powerful. And then our moving to the right, I usually spend a little less time talking about these, but the slice right in the middle, that's a poorly managed pasture, has a lot of bare soil, has some compaction occurring. You can see we got about a half a bucket of runoff from that. And then the next one to the right is a well-managed pasture, which has about a third of a bucket and almost a full bucket in the back of infiltration. And then the one furthest to the right, that's a permanent hayfield, and we have a full bucket in the back. So lots of things happening here that you could talk about for a long time. Next, I think it's really important, especially as we talk about how we talk about how runoff is produced. And there's really two different mechanisms. We have infiltration excess runoff. And that's the typical way we conceive of runoff occurring. And it was discovered by this guy, Horton, who's was a civil engineer, but you can kind of see, I think the image on the lower left corner of your screen kind of provides an example of how this runoff occurs. It's raining much harder than the soil can infiltrate, right? The rainfall rate is higher than the infiltration rate. So we start to get runoff. Okay, that's typically how we conceive of runoff occurring. The other way runoff occurs is saturation excess runoff. And this, believe it or not, outside of the Champlain Valley, outside of our heavy soils into the hilly topography of Vermont, this is the dominant way that runoff is produced. And this is very different than infiltration runoff, the kind of the conventional way we think of runoff. Saturation excess runoff is where there is very, very high infiltration rates in the soil because it's fairly coarse, but there's a limited amount of space within the soil. So the soil actually fills up because there's a restrictive layer within the soil. And when that soil fills up, it completely saturates all the soil. So no more incoming rainfall can actually soak into the soil. And then we start to have runoff. And this happens in a lot of I'll mention them later, our fragipan soils or Cabots or Perus. And it often occurs in sloping topography at the base of the slope. So you could have a lot of rainfall occurring. This kind of goes back to your question, Lauren, about how slope influences infiltration. Even on these sloping soils, these hill slopes, lots of capacity to infiltrate water, and then that water flows downhill underground and then saturates the soil at the toe of the slope. And then any addition on that saturated area becomes runoff, and that's where the runoff is generated in these fragipan soil sloping terrain areas of Vermont. So really important to be aware of this, I think, if you're working outside of the Champlain Valley. And Vermont has a notch in its belt here in terms of the history of hydrology, because this type of runoff was discovered in the USGS Sleepers River watershed in Danville, Vermont in the 70s. And then Thomas Dunn was really the kind of the leading mind behind that work. And it changed. It's all of a sudden, once we understood how runoff could be produced this way, we started to see this elsewhere within the country and the world. And so it really changed how we think about and how we model and account for runoff being produced in some areas. So just a neat little piece of trivia there. Okay, so I'm just going to check my watch here, about 3 o'clock. Okay, so that's runoff and erosion. Now I want to present this, like I said, a cautionary tale of phosphorus, soil health, erosion, and water quality. I didn't go into depth about it, but we have all these management practices that we can use. And I think you've already talked about reduced tillage in agriculture. And so I didn't spend a lot of time on that. How we can use those practices to reduce erosion. That's fantastic. But there have been some concerning findings related to that widespread usage of those practices. And I'm in no way saying we shouldn't use those practices. I'm saying we should be aware of the potential trade-offs and vigilant for what could potentially happen. These were first noted in the Western Lake Erie Basin. That's an image of Lake Erie there as they started to see increased frequency of algal blooms within that lake, and they had a really strong history of adoption of reduced tillage and soil health practices within the basin. And that was fantastic at reducing erosion within and particulate bound phosphorus transport within the watershed. And it significantly improved the water infiltration and reduced runoff. And a lot of these soils were tile drained. So as I mentioned before, we had these biopores forming and lots of water not running off the surface, but traveling down into tile drainage. But what the other thing it did, it also increased the stratification of phosphorus in the upper soil layers because we were no longer mixing the soil. The phosphorus bonds really tightly to soil particles. And so when we apply it on the surface, if it doesn't run off, it pretty much stays in the surface soil unless it's mixed in, right? And so when we weren't mixing that soil, we weren't tilling that soil, they started to see this. I keep saying we, it's not we, it's they. They started to see this stratification of phosphorus. And here's just some work that shows stratification in Wisconsin from long-term no-till. And the blue bars are the shallow soils. And you can see that just, these elevated concentrations of phosphorus in these surface soils from long-term, from really the cessation of mixing of the soil, of tillage of the soil. So you have all this phosphorus sitting right there in the surface of the soil. And then I'll go ahead and go on to the next slide, I guess. What they started to observe is that they were seeing more dissolved reactive phosphorus being transported to the lake, which was more bioavailable for the algae. And so they had these algal blooms occurring, even though they'd done a fantastic job at reducing particulate bound phosphorus because they'd stratified the phosphorus in the upper layers of the soil. And when they did have surface runoff occurring, it was interacting with those really high P soils on the surface, or water was running across the surface, picking up soluble phosphorus and then traveling down through the macropores into the tile drainage. They were seeing now an increase in the soluble P transport. And this figure is from the Jarvie paper, which was the really kind of the seminal paper that started to unpack the issue within the region. And I don't think we're there yet in Vermont in any way, but I think it's really important to be aware of these unintended consequences that occurred within other areas of the country. And it's just I'll explain this a little bit more. I apologize. The blue was the soluble reactive phosphorus transport before really widespread implementation of conservation practices. And then once all the soil health practices were kind of ramped up, and the particulate phosphorus was decreasing, you started to see then from 2003 onward this increase in the soluble reactive phosphorus transport, which is what was really driving the algal blooms. Okay. The next topic that I wanted to address was soil compaction. And this is kind of I think a really exciting topic, a really kind of a pet peeve mine, a pet project, if you will, because of clay soils in the Champlain Valley. We have high risk of compaction, and compaction is really a compression of the void space within the soil. And I'm showing top left there, you see an undisturbed soil versus a compacted soil. In an undisturbed soil, kind of rule of thumb, maybe you would have 50% of the soil being void space, roughly. In a compacted soil, you've really reduced that to about 25% of the void space. So there's less opportunity, there's less air, oxygen for organisms, and there's less water holding capacity within that soil as well. Soil compaction becomes worse when soils are wet. And this is especially true with the clays. And this is just a kind of a classic ag engineering figure that shows compressive forces or compactive forces beneath a tractor tire on a hard, dry soil, a moist soil, and then a wet soil. And so as that soil stays wetter and wetter, we see those compactive forces traveling deeper and deeper. In a dry soil, you see more friction between the soil particles. And so it helps to prevent the transmission of those compactive forces deep within the profile. In a wet soil, the soil particles slide past one another. If the soil voids are full of water, they transmit those forces downward, and you just see more of the forces going deeper and deeper and causing deep compaction, which is the really most ornery type of compaction, is that deep compaction. And then we do a lot of work around climate change, and so we think that climate change and the increased amount of precipitation in Vermont is leading to really this becoming even more challenging than it was to avoid compaction, because we have just so much more a longer period of the year when soils are moist. And then compaction also affects infiltration rate, which of course would then affect runoff rate, right, or runoff volumes. And this is a figure from Stormwater Manual of Minnesota that shows how a compacted soil has much lower infiltration rates than a native soil. And of course, compaction also has effects on yield as well. This image on the left is showing how compaction prevents root penetration. These are corn roots in a compacted soil and then uncompacted soil, and that compaction and inability of roots to travel deeply and access nutrients and moisture at deeper depths also affects yield, which you're seeing there in that study from the Midwest, from the University of Missouri. Up to 55% reduction in yield because of compaction. So it's not insignificant. It's meaningful amounts of impacts on yield. And then dealing with compaction, and this is where we've done a little bit of research here. Compaction is, it's not something that goes away on its own. They found compacted tracks, wagon wheel ruts from expansion from wagon trains even to this very day. So once we have compaction in some soils, it doesn't necessarily fix itself. It may require some sort of intervention, and there are various ways of doing that, right? We can try to use biological approaches with various types of crops, cover crops, things like that, or we can use mechanical approaches. And we've done a little bit of work in this area in both corn and sod systems, and I'm just going to show some of the work from the corn systems. So this is an aerial view, really cool aerial view taken with a drone of different cover crop treatments. And we had a variety of treatments, but really several of these were targeted toward selection of species that would help with alleviation of compaction. And we're using soil health as a measurement of compaction as a proxy for compaction. So we had winter rye, we had tillage radish, which is the daikon radish I showed in the last slide. Is that big white radish. We had annual ryegrass mixed with tillage radish. Annual ryegrass is there's been some research looking at the penetration force of roots and annual ryegrass rates really high up there in its ability to puncture through wax plates. So we thought that might be very effective at moving through compacted soils. A mix of winter rye and tillage radish, winter rye, oats, and tillage radish. And I'm just circling the ones there at the bottom. And then we also had plots of mechanical treatment with using a subsoil tillage tool, and these are used, in the Champlain Valley across Vermont, and some in sod systems and some in corn systems. This one was done at a 20-inch depth. And just a kind of a quick note on this, we've talked a lot about subsoiling with farmers this fall, and I think if you do choose to subsoil, it's very important to note that timing matters. It has a very has a controlling influence on the effectiveness of your subsoil operation, because if you subsoil when the soil is still moist, you'll just end up slicing through the subsoil, and then that's just wasting diesel, right? So we try to recommend that you dig down to whatever level in the soil where the compaction exists. If you can make a snake with the soil's too wet to subsoil, but if it is dry enough that it won't create a snake in your hand, then it's dry enough that it'll fracture when you use the subsoil implement. And that's really the point at which you might start to get some benefit for compaction remediation, is when you see that fracturing occurring. Okay, so back to the research. So we did this at 20 inches in plots, and we had a little bit of a data collection error here, but I'm showing soil health values from year 1 and year 3, and really the deep tillage treatment was the only treatment where we saw a decrease in the soil health, and we attributed that to inability to alleviate compaction. In every other case, we saw an increase in soil health using the Cornell soil health scoring system, the CASH system. Okay, we're at 10 after. Looks like I have another break built in here, and Q&A, and maybe we also just go ahead and maybe take 5 minutes, whatever you recommend, Lauren, for a quick bio break as well.
Yeah, do you want to do questions before the bio break or after?
Oh, we can do it before. We'll see. Yeah, how many there are.
This question from Dorothy. Thinking back to your pictures of gully erosion, what are the next steps a farmer can take to address gullies in their fields in terms of practices to reduce future gully erosion, and also what they can do with existing gullies? So those pictures are pretty daunting.
Yeah, those are bad. Yeah, I mean, it's interesting. We have a project starting up this year that's going to look at targeting of practices to address gully erosion, but really, we don't need to wait on that research to come through. Like, any practice that is going to help increase soil aggregation and soil infiltration should help with gully erosion, gully formation. So all the things we discussed, really, that's helping get water into the soil and prevent it from running across the soil, preventing, increasing infiltration, decreasing runoff, because the runoff is really then what starts the process of a gully formation. They start at what we call a nick point, and then once it starts, it's really hard to stop. So it's really about soil management for prevention of even just the start of a gully. Once a gully is formed within those fields, well, let me back up. So the other way, if there's an area of a field that has been prone to gully formation, it may be a good candidate also for to transition that area of the field into sod, like a grassed waterway, a vegetative waterway, so that's not in bare soil. So that's another approach. Once the gullies are formed, the only approach I know of really to kind of try to remediate them is to do some smoothing. But if you know, that's the time where it might be very wise to, if you feel like it's a place, a candidate for reformation, to put that seed that down, get some mulch on it, and get it into a grassed waterway so that it doesn't form again. We call these, you know, a lot of these gullies reform year after year in the same location. Those are especially places where it's a, you know, we need to do some seeding down of those areas.
Wonderful, thank you. There's also a question from Daniel. Daniel, feel free to hop in too if I'm not getting this right. Is the evidence for periodic tillage to break the phosphorus? I'm assuming that's referring back to the study.
Yeah, great question. That is, you know, that is one of the approaches that they're potentially recommending in some instances. And I know they were starting some work on that. I don't have the results of that study off the top of my head of kind of a limited tillage, a targeted tillage type approach to try to get that phosphorus mixed in. But that's absolutely something that was on the table within the Western Lake Erie Basin.
And then I actually had a follow-up question on that. Is there anything you can apply to the soil to kind of immobilize that top layer of phosphorus?
There, you know, they've tried some even, you know, we've even tried some things in Vermont. I wasn't involved in it, but they tried gypsum, which does immobilize phosphorus. Um, I don't, you know, and they've had some really good success with that in some Kevin King studies out of Ohio. I don't understand why it hasn't been promoted more, if it's a cost issue. But there has been some promising work, but it doesn't seem to have caught on with, you know, in terms of common practice. But that amendment, gypsum, is maybe the one that I've seen studied the most.
Okay. And then Kate, who's signed in as me in the chat too, just so everybody knows I'm not asking my own questions in the chat. Kate asks, when thinking about nutrient loss and tile drainage, which factors have the most influence? Do management decisions like tillage, perennial versus annual crops, and manure incorporation and injection offset some of the soil properties, like texture and type, that might cause more nutrients to be lost through the tile drains on some fields compared to others?
I'll tell you what, I will ask Kate to hang on, and we're going to get into that in this last section. And then if there's still lingering questions, glad to answer. But I think I can probably do that question more justice with some of my slides coming up.
Perfect. And I've got two more questions for you. You know, in Vermont, there's a lot of wetlands that have been turned into fields. And I guess I'm just wondering if you can speak to, you know, we often see a really high organic matter on those fields. And are there ways to really identify what field is really a wetland versus not, just from doing some field observations?
Well, I'm going to leave that up to NRCS wetland delineation scientists and their teams there. I know, you know, looking for redox features and vegetation characteristics and duration of saturation are some of the things they look for. But you know, I'll leave that up to them. You know, I know there are some converted wetlands. A lot of the drain, I mean, if you're referring to drainage, a lot of the drainage I see is not of wetland soils. It's just of really poorly drained, you know, of soils, but not what I think would be considered as wetland soils. Just really heavy clay, slow draining soils.
And then I just kind of wanted to reiterate the point you made that the hydrologic soil groups are really related to percolation, but it doesn't necessarily they don't necessarily account for infiltration. I thought that was really important. I know that's something that, well, it's a soil, it's supposed to infiltrate really quickly, but it's really depends on that surface layer.
Yeah.
I just wanted to reiterate that because
Yep, that's a
yeah.
critical point. Yep. You can have a really high, you know, very permeable soil, but if it's crusting occurs, then water does not move into or through that soil. Yep.
All right, those are all the questions we have right now. Do we want to come back at 3:22 for the rest of it?
Sounds good.
All right, we'll see y'all back here in a few minutes.
Share my screen again. All right, welcome back. The last section is on irrigation and drainage, so water management, less so soil management, and so water management. And so I don't have a ton to say on irrigation. Like I said, it's this is important for specialty crop growers in the region. But it's you know, it's I think we're as uh, service providers, it's kind of newer to us. There's not a lot of the institutional knowledge that exists in drier parts of the country like California and the Southwest, and so we're still learning. Um, so I'm going to lean on your kind of your quote unquote textbook for this course from my first slide here for good irrigation management and just walk through some of these bullets and then talk about some of the research we've done with looking at water use efficiency in irrigation systems. And I think that's really just good background information to know if you're working with a farm that utilizes irrigation. Okay, so first bullet here, I didn't include all the bullets because I don't think all of them were necessarily that relevant for our region, but these are. Building soil to be more resistant to crusting and drought. Of course, this is everything we talked about up till now. You know, trying to incorporate organic matter, maintain structure, keep soils covered to prevent crusting. All these things, you know, as they help with infiltrating rainfall, they also help with making sure irrigation water gets into the soil where it belongs and preventing the runoff of that soil, and then also increasing the water holding capacity, right? Increasing the moisture that can be held after drainage stops from filled capacity down to the permanent wilting point. So it lengthens that piece of the soil moisture continuum. All right. Monitor soil, plants, and the weather to precisely estimate irrigation needs. I will talk a little bit about monitoring approaches and technologies in my slides here. Using precise water application rates. Do not over irrigate. Over irrigating can be just as it can have downsides as can reduce tillage and leave surface residues. I think we've talked about that extensively. Mulches also, as they function to help reduce aggregate destruction, they also reduce surface evaporation. Integrate water and fertilizer management to reduce losses. So that means promoting fertigation systems where the fertilizer, the nutrients are mixed in with the irrigation water. Prevent salt or sodium accumulation by applying basic principles of salinity management. Testing soils. This is really not an issue. Salinity really becomes an issue in irrigated regions that don't receive a lot of rainfall precipitation outside of the growing season. And what happens in Vermont is if we do have salinity buildup from irrigation for some reason or another, it all leaches out during the winter time because we receive quite a bit of off-season rainfall and percolation. But where this can become an issue, and I think high tunnel growers should be aware of this, is in high tunnels where we have the soil covered and we're not receiving that off-season rainfall to leach out any salts that could accumulate. So something to be aware of for irrigation in high tunnel systems. All right. Okay, so I'm just going to jump into some research we've done that looks at just basically trying to put brackets around how efficiently farms are utilizing irrigation water in Vermont. And this study goes back to 2018. We did about 3 years of research on several different farms, and I'm going to focus on one farm because I think it nicely ties up our results from the entire study. So this farm had a little over 30 acres of mixed vegetables. They're on some pretty nice alluvial sandy loams, had reliable surface water, and we did water use efficiency calculations on 26.5 acres that were receiving overhead irrigation. And then we did it separately on 4 acres that were drip irrigated. And we had various tools to do this and use some modeling approaches as well. And so I'll start with the overhead irrigation, and just to explain to you quickly what you're looking at. This is an estimation of water deficit. And so the x-axis is 0. That means 0 water deficit. And when the green line is below the x-axis, it means we have a water deficit. And when the green line is above the x-axis, it means we have a water surplus. And then the red bars and the blue bars are rainfall and irrigation additions. And the deficit is really calculated through evapotranspiration calculations. We had some tools out there to measure evapotranspiration, or what amount of soil water the plants are actually using. Okay, so for the overhead irrigated fields, we used about 840,000 gallons of water during this period. That's about 32,000 gallons per acre, and we saw a deficit of 2.6 million gallons and a unit area deficit of 100,000 gallons per acre. So this farm could have with tools and adequate infrastructure, could have utilized another 100,000 gallons per acre of irrigation water. So again, this farm is not using any tools, which is typical of many farms in the region. So it kind of shows you what's possible in terms of under application. And then my next slide is on that 4 acres of drip irrigation. And on that 4 acres, they used a little under 1 million gallons of water. 236 gallons per acre. They had a total over application of 368,000 gallons of water. So you can see that green line that measures deficit or surplus is in the surplus zone most weeks of the year, and you can see how much more irrigation water they applied using drip irrigation nonetheless. And so they actually ended up using a surplus of about 100,000 gallons per acre. So really, that's why I say I think this farm brackets what might exist on Vermont farms, because on one hand we saw some areas of this farm under applying by 100,000 gallons per acre, and another area of the farm over applying by 100,000 gallons per acre. So just, we measured farms that are anywhere in between. So it's just, I think, good to be aware of where water management is, and that there's a lot of room for improvement. And so how do we do that? How do we improve our water management? We can do it a few different ways. And probably the most direct way is to actually measure the soil moisture. And there's two different tools that are common to do that with, and I'll show you that in just a second. But if you use these tools, it's likely that multiple sensors would be recommended. So, multiple locations across the fields or the farms. You'll have different soil types that are going to dry out quicker or slower than others. You have crops that use water at different rates than other crops. So just making sure you have good coverage with your sensors. Some of these sensors, the cheaper sensors, most basic sensors require manually reading them. So you have to actually do the legwork to walk around and look at your soil tension. And you really need to monitor the soil tension, especially around irrigation, to make sure you're not under irrigating or over irrigating. And simple, these are simple, but I think they're great for understanding if we're in the ballpark. And you can, on my previous slide, you can see this farm was not in the ballpark. On the other, either side of the ballpark, but not in the ballpark. And so these can really help us tighten things up. They're not the technology that's used, in a lot of the big operations in California where water is, gold, but they can certainly help. So our first option here is a tensiometer. And I saw this was mentioned in the Magdoff NS book. This just simply measures soil tension. I think we talked about soil tension in our few slides on soil water. That's how much suction the soil has. And this just has a gauge on it that measures soil vacuum, soil tension. They're about $70 a piece. Been used for years and years and years. They are a little fragile, I find. They do require a little O&M, but there's no electronics, and they work pretty well. The other option are these granular matrix sensors. These don't really have any O&M. They're about $35 a unit, pretty durable, but you do have to have a $250 reader to hook up to these to walk around and see your soil tension. But both work reasonably well. So there's a couple options there. And then there's like I said, there's other systems that are used in other parts of the country, web-based network of soil moisture sensors. We've trialed 3 or 4 of these types of systems where you can look at the soil moisture at various locations on the farm on your smartphone. Fantastic in theory. There is a learning curve with the technology and a significant cost. I'm not really recommending these for Vermont farmers given the cost and the fact that in every year these would not be utilized. So there's I think there's less less bang for the buck than something that you would use every single season, where a wet season like 2023 you probably would not be utilizing these at all. And the technology is, unless the farm has someone dedicated to irrigation management on that operation, it might be a little bit tricky for someone to kind of keep up with, in addition to all the other farm tasks that have to occur, right? Because the technology is not all of it is exactly plug and play. But they do give you the real-time sensors systems. They do give you a continuous measurement of soil moisture. And that's what I'm showing here, just a snapshot of a couple weeks of soil moisture sensor readings. One is showing the red bar, horizontal bar at the top is showing these 3 crops, the carrots and the carrots and the onions all went above the recommended soil moisture tension, meaning they're getting very dry. So you can see this in real time. And then the red circle at the bottom, this is where the soil moisture, this is where the farm is actually over irrigating. So the soil tension is dropping and flatlining when the soil is saturated, and so we knew we were having leaching occurring during that period of where we see flatlining saturated soils. So you get lots of information out of these because you see what's happening with your soil moisture real time and day by day with each irrigation cycle. Okay, so that's irrigation. Now I'm going to jump into drainage. And this is a big topic in the state, in the region, and it's not new that it's a big topic. I love this quote from the annual report of the Vermont Ag Experiment Station 1912. It's not whether one can afford to drain, but whether one can afford not to drain. So I know we're talking a lot about drainage, and climate change is making that ever more important. But Vermont farmers have always knew that drainage had value, and they've been trying to do it for some time. All right, benefits of drainage. Lots of work done in other parts of the country. The big 2 benefits are really improves crop production and gets you off the roller coaster of wet years and dry years. It helps level out yields and just gets water out of the root zone and helps crops be healthy and productive. And then the other one, the kind of the unsung benefit is improved trafficability, which can have many follow-on benefits, right? You know, it allows a farmer to get in the field and do what they need to do when they need to do it, you know, plant when they need to plant, harvest when they need to plant, other operations when they need to do it without damaging soils. So this has, you know, those benefits to yield as well, and other benefits. Just showing some data there from drainage studies that show, you know, the benefit of drainage in agriculture, from Ontario, and then the longest running study I'm aware of there in Ohio. It does not, drainage is not always tile drainage. I don't mean to give that impression, especially in hilly topography. There's lots of other options that can be utilized instead of tile drainage. Some of them much more cost effective than tile drainage, especially in sloping landscapes. We have, you know, the option of doing interceptor drainage type interventions, where we have berms or swales at the toes of slopes to divert water before it enters the level production area. That can be done with kind of lower left there with an excavated ditch at the toe of a slope, and or it can be done like on the right-hand side of your screen with a gravel-filled trench. Both of these work. The gravel-filled trench, of course, has the benefit that you can then drive across this with a tractor. The gravel-filled trench picks up surface runoff as well as subsurface runoff. And I mentioned this type of soils we have in Vermont, the fragipan soils. These types of drainage interventions work really, really well for picking up that subsurface flow and moving it away from the toe of the slope before it enters the flat area, which in most farms is where the production is occurring, and where we have the drainage issues to begin with. And then of course, there is tile drainage, and it's not new. You know, it's been around for a long, long time, as has drainage. This is a quote from Cato in 200 BC. Well, I don't know the quote, but a reference. So it's, you know, farms have always known the benefit of drainage. It used to be clay. That's what I call tile. Now it's this perforated black plastic pipe placed about 3.5 to 4.5 feet in the ground beneath the root zone, and it just serves to lower the water table and move water out of the soil and away from the crops. I mentioned this slide. It really removes the free water or the gravimetric water. This is, of course, that demonstration I mentioned with the sponge. Tile just removes the water that would drain via gravity, but it doesn't take out the water that you would then squeeze. As you wring that sponge, I equated that to the crops sucking water out of the soil. So tile does not remove that water that is available for crops. That water remains there for crops to use, because all tile does is remove that free water or gravimetric water. Tile is drainage. This goes for drainage and tile. You know, I keep saying tile, but I really mean drainage. It doesn't remove plant available water. I mentioned that, but it works in dry years and it works in wet years. In the wet year, of course, it keeps water low throughout the year. In the dry year, it'll help keep early season in the spring to allow establishment of deeper root structures, so that later on, when it does get dry, you have the deep roots to access water. Whereas if it was an undrained soil, those roots never would have established at a deeper depth in the early season, so they're not able to access deeper moisture in the late season when it does get dry. You know, spacing is really important for drainage. Probably the most important when we talk about tile drainage is really important for its benefits. This is some work done from extension associate at Cornell, no longer there, Larry Gehring, that looked at different spacing for various forage crops. And you can see that the influence of surface drainage versus tile drainage at 100 feet and then tile drainage at 50 feet, you see this dry matter yield increasing across that gradient. Tile drainage can be installed in various different patterns, from parallel to herringbone. to random. We have a lot of, we're seeing more and more pattern systems being installed in Vermont, especially in flatter areas. But there's a tremendous amount of random drainage out there that could be, in many cases, 100 years or more old. It's just, you know, where there were depressions, farmers used to go in and put in one line of tile into a field, and there's a lot of that out there across the region and across the country as well. Like I said, tile spacing is really important. How do you determine what spacing should be used? There is an NRCS drainage guide for most states. We did have a Vermont guide. I'm not sure that it's been updated in a long time. And a lot of the spacing that I see being installed now by farmers is a little bit tighter than what's recommended in the drainage guide. So so it may need updated if it's going to continue to be used by NRCS. It can be calculated based on the soil type. I recommend really just relying on local knowledge, other farmers and contractors' advice in terms of spacing, just understanding what's going to be effective in the particular soil type that you're interested in draining. But it does have financial implications. The closer you put the tile, the more expensive it is because the more tile you're going to have installed in a particular field. The importance of soils. So this is where I love to make this point about there's various soils in Vermont that have a fragipan or a densik layer at 20 to 30 inches or so. Cabot Peru soils are very good examples of that. And if the tile is placed into the densik layer in these soils, it will not drain water from the upper layers. The soils will tend to crust over that tile and kind of encapsulate it. And it won't function to drain soil from the upper layers. So it's really good to understand what type of soil you have when you go in to drain a particular location, and if the tile needs to be placed above that densik layer. And then some miscellaneous items. Really with the drainage system, you have to start with the outlet. You have to make sure you have an adequate outlet to move water out of the drainage system. Once you've established the drainage system, needs to be at least 2.5 feet deep. Pipe material, you can have a double wall or single wall. A double wall has smooth lining, and it can move water more quickly, so it's less likely to accumulate sediment within that pipe. So if you have a low slope system that's water's not going to flow very fast, a double wall pipe might be recommended. Lots of different design factors that a contractor can help with. Do you need a filter sock on it? Do you have soils that are likely to migrate into the drainage tile system? Things like that. There's lots to consider there. And then, we can't really talk about tile without talking about environmental concerns, and that's what I'll spend the rest of my time on here, because I do quite a bit of work on this. We used to think that there was really no phosphorus transported in subsurface water and tile drainage water because we know that phosphorus bonds really tightly to soils. And so we didn't think that phosphorus would move downward far enough into the profile to move into tile, but primarily because of preferential flow, those biopores, macropores cracking, we do see phosphorus moving downward into tile lines, and that's been noted. There's a citation of Kevin King's review paper from 2015. Lots of work done by his research group there, looking at the amount of phosphorus that does move into tile drainage water. And then, of course, Vermont has been abreast of the situation with new drainage rules and funding some reports and funding research as well. So what does the scientific literature say about phosphorus and tile drainage? And these are just a few 6 or 9 highlights, I think, are kind of key takeaways from the literature. Most phosphorus load comes from storm events and high flow, and we've seen that in Vermont as well in our work. In some cases, over 96% of the phosphorus is being transported during a storm event, not during a slow drain of the soil profile in between storms and in the springtime. Most phosphorus load occurs during the wet, cool, non-growing months. Very true. That's also what we've seen here, that it's not high loads in the summertime. It's really during the non-growing season, when we have really wet conditions. 2023 is an exception, but we're seeing most phosphorus being transported in the non-growing season. No-till and sod systems have higher P loads than tilled systems. This is because of just that phenomena that I mentioned, the formation of biopores and macropores and a lot more water, and stratification of phosphorus in those systems. Okay, second row, higher soil test phosphorus has higher phosphorus load. So that's a given. As we have more phosphorus available to be transported, we're going to see more phosphorus transported. Soil prone to preferential flow have higher P loads. So those well-structured soils, those shrink swell cracking soils, that's where we see the preferential. That's where we see high loads in those preferential flow path soils. Deeper tiles have higher loads but lower concentrations. That's because we have the water filtering through more of the soil profile. So there's more opportunity to remove phosphorus as the tile gets deeper and deeper, but we have more overall water. So even if we have lower concentrations, the more overall water outweighs that, and we end up with higher loads in that discharge water. Tile spacing does not have a significant influence on water quality factors. Fine textured soil more strongly sorbs P, like our clay soils, but loss is still greater in coarse soil due to preferential flow. Higher water table, reduced conditions lead to phosphorus loss. So as we see more saturated soils, we see anaerobic conditions forming in those soils. And when we see those reduced conditions, phosphorus starts to desorb from the soil, and we can see some increased phosphorus loss. Okay, so what does, and then here's a slide I borrowed from Kevin King that's speaking to what do we know about basically the 4 Rs, nutrient management and phosphorus loss in tile drainage. So just a few learnings. Organic phosphorus, like manure, tends to pose a greater risk of leaching compared to inorganic P. That's because it is a slow release source of phosphorus, and we don't target it like some of the synthetic sources to exactly how much the plant needs and when the plant needs it. The potential for phosphorus transport to tile drains increases with an increase in P application rate. That's pretty intuitive. Phosphorus losses in tile drains are greater when phosphorus is broadcast on the soil surface compared to incorporated, and that's maybe a little counterintuitive, but when we broadcast manure phosphorus on the surface of the soil, it can then run off into those preferential flow paths and straight down to the tile. But when we mix it into the soil, we allow for more surface soil to phosphorus contact and more opportunity to sorb with the phosphorus. Number 4, a greater risk of P transport to tile drains is found when phosphorus is applied in the winter compared to the spring and the summer. And this is just, again, fairly common sense. If we have that phosphorus sitting there all winter, crops not using it, it's going to be subject to loss. And then rainfall right after phosphorus application also increases the risk of P transport to tile drains. So a few takeaways, many of them, I think, what we might guess around the 4 Rs in tile drainage. And so it's complicated, right, with tile drainage. And I want to make this point that it has been known to decrease surface runoff. And it's been known for a long time to decrease surface runoff. And this is, after we had our first section today, this makes sense, right? Where as we drain that free water from the soil profile, that gravimetric water, we're creating more space within the profile for incoming rainfall to then soak in. And that rainfall that soaks in cannot become runoff. So we're decreasing surface runoff but in turn increasing subsurface runoff. We also see, because we're decreasing surface runoff, anecdotally, that we're decreasing surface erosion in some cases. And improved yields mean with drainage, especially in like a summer like 2023, means more phosphorus is removed by the crop. If we don't have a healthy crop, we're not removing phosphorus from the soil. And then tile drainage, Heather Darby did some survey work, and found that farmers reported that tile drainage really increased the opportunity to adopt soil health best management practices. Because the soil was drier, they were less likely to compact the soil with no-till. They were able to get on the field, even if it was wet, to plant cover crops, things like that. So like I said, it's complicated, and we don't know all the answers and kind of the net effect of tile drainage in the basin. And then I'll leave you with this slide before I stop. If anyone's really interested in tile drainage, you should head to Geneva, New York on your next vacation and visit the Drain Tile Museum. It's loads of fun. So I'll stop there, and maybe we have some questions.
We do indeed. Thank you again so much, Joshua. We got a couple questions in the chat. This one's from Kent. Considering the high rainfall and lack of soil freeze, we are expecting to see many farmers revert to conventional tillage to remove ruts from working wet soils last fall. What practices would you consider to address compaction issues during this upcoming season?
Yeah, great question, Ken. It's going to be a really tough. We're going to see setbacks in soil health from this past season, and then efforts to try to repair, just deal with ruts and damaged soils. I wish I had a good answer for you. I mean, I hope it's dry, that when farmers do get a chance to get on the field and do some repair work, and I know they need to, that we're not creating more damage and more compaction. That's all I can have to say. Yeah.
And then a question from Charlotta. Are you able to do a quick tensiometer reading as you walk a field? Are those sort of tensiometers available? Do the $15 tensiometers do anything?
Yeah, no, not with the tensiometer. They require some time to equilibrate. There are some soil moisture probes that you can carry, but what they do, they give you a volumetric water content, and that's not as meaningful from an irrigation standpoint. Most irrigation scheduling, you really want to understand the soil tension, and not the gravimetric. I know that's a complicated answer. You can calibrate your soil moisture probe, but it's a little more complicated. It's not so straightforward.
And then another question from Charlotta. If we do a bit of tillage to mix in the phosphorus, what effect does that have on nitrogen and groundwater? I think specifically related to manure incorporation.
Yeah. I don't think that would have a negative effect on nitrogen in the groundwater. It's interesting in the like the Mississippi Basin, they're not concerned about phosphorus in the tile drainage. They're concerned about nitrogen, and anything that decreases the amount of infiltration and percolation reduces the amount of risk of leaching of nitrogen. So I think soils, we're not going to have a negative effect on nitrogen in our tile water.
Then I just got a couple other questions for you. You said this, and I just wanted to hear you say it again. That leaching occurs at saturation, so you're not leaching any nutrients if you're between saturation and field capacity. Is that correct?
Yeah. Well, if you're between saturation and field capacity, yes, you are, but it becomes much more pronounced at saturation. I guess I'll say that. That's when you're really losing bulk amounts of water. Yeah.
Wow.
There is still downward drainage occurring between saturation and field capacity. Yeah. So the target with irrigation would be hopefully bring it up to field capacity. That's the target, right? And if you see you've gone to saturation, you're way beyond the point of leaching. You've definitely leached some water and nutrients.
And then related to that, under saturated conditions, is surface erosion more likely?
Yeah.
Yes. Okay.
Yeah.
And then I know we don't have a ton of time for this, but obviously ditches and that type of approach is good when you're talking about kind of surface runoff, but I know a lot of farms have also like straightened channels that are streams, and I was wondering if you could just speak briefly to the difference there.
Between a stream channel and a ditch.
Yeah,
Yeah, I might rely on my regulatory friends to make that for that conversation.
fair
I
enough.
know, yep. Yeah, I think I know there are rules around what we can do if something is a perennial flowing waters. So I know I don't, I feel uncomfortable answering that one. Sorry.
Fair enough.
Okay.
Um, Wonderful. Thank you very much, Joshua. If anyone else has more questions for Joshua, please put them in the chat or put them in the evaluation form. I just tossed that link in the chat. And to end today, I'll do the usual what's coming up next week. Like I mentioned before, coming up next week is integrated pest management, and we'll have Anne and Steve, and they are definitely experts on the topic. We'll learn a little bit about plant pathology, and then also we'll talk about pesticides and neonics and all the things related to managing pests related to soil health. The homework for next week is to read chapter 8 of the Magdoff and Van Ness book, Soil Health, Plant Health, and Pests. I do also want to do just a gentle plug. We've been getting some awesome resources from folks after each webinar. And so if you are interested in a certain topic, we have been back adding some really great resources into those recommended resources sections on campus. Specifically, the grazing one last week, we received a really great resource from Tom that's posted on that campus website now. Please do take a look. And then we also added some resources back to the Living Soil webinar that kind of give a broad overview of what we do and don't know about using biology to measure soil health. So those are really great resources that if you haven't looked at them, please do. With that, I am just going to thank you all again for being here and being involved in this. Really excited to have 3 more webinars with everyone, and deep thank you to Joshua for your knowledge and everything that you're doing on the landscape to help us better understand water management, specifically in Vermont. Thank you, everyone, and have a great rest of your day.